So to start with, if I used this thought process to say 1 is to 2 as 2 is to 4, that's a direct variation, and I could continue that trend by finding out what the constant is. In this case, the constant would be 2. The output is 2 times whatever the top is. Okay? So in this case, the constant would be 2. Now, inverse variation. I don't know, I told somebody yesterday that speed and time are inversely related. The faster I run a race, the shorter my time will be. The faster you drive, the quicker you'll get to grandma's house, right? So you could say that as my speed increases, the time it takes decreases, and that is what inverse means. Inverse means as one thing goes up, the other thing goes down, or as one thing goes up, the other thing goes down, depending upon what you're talking about, right? So they use this equation. This here, what this is showing, instead of the relationship looking like this, the relationship is inverse. If you use the letter M, it's M over X, if you're thinking that way. Instead of M being multiplied by X, that constant is being divided by X because it's inverse variation. Now, the easiest way to do these is simply to practice them. And when I was learning these years ago, I literally would write like a sample of this, a sample of joint, and a sample of inverse, joint, and direct, and just keep looking at them until I had it memorized. If you have to do that, do it. So for inverse variation, K is the constant, and that's going to be the same thing for joint variation, okay? They're going to have it written with a K as well. Again, I didn't choose the letter, that's just how they're writing it. The key to discovering what kind of a relationship you have will be looking for the words direct, the word inverse, or the word directly to, which is also basically saying direct, okay? So you're going to see all of those mixed together eventually, but example 1. Example 1 says this. If y is inversely proportional to x, so that's this situation here. That's direct. This one is inverse. If y is inversely proportional to x and y is 6 when x is 5, find x when y is 12. In order to do this, I first have to find out a value for k. X is inversely proportional. If y is inversely proportional to x and y is 6 when x is 5, find x when y is 12. Once I find k and plug it in here, I can solve for x. Most of you can probably already see that k is 30, but for sake of argument, it's going to look like that. Okay, and they've already shown us that. We're going to use k here. And depending upon how you, in your mind, view these, I know that this means that. And when I divide, I'm able to discover that x is 2.5. Okay, and that would be your answer. So unlike the constant ones where you can usually just see it, these aren't quite so simple. So the ones that were constants, remember I didn't force you to find m. I knew you could cross-proportion it and figure it out. These you have to find the constant. Otherwise you're going to end up with answers that don't jive. Okay? I'd like to do a couple more samples like this, if you don't mind, because one example for me just wasn't enough back in the day. So here's another example, okay? I'm still going to call this example 1. It's my example, but we're going to use it nonetheless, okay? If y varies inversely as x, so they're describing the same situation, and y is 3 when x is 6, find x when y is 18. Okay. Y varies inversely as x. There's the equation. If that's true, and I know y is 3 when x is 6, find x when y is 18. First, we have to obtain our k value. You can see right here, k is going to be 18. Okay, and if k is 18, then if I plug in over here, I know that 18 divided by something is 18. You all know the answer is 1. Okay, that would be your answer. And you could solve for y as well, depending upon what they gave you. Okay, find your constant, plug in, and solve for the item they're searching for. Here's one more. I don't know if you guys recall from yesterday, something varied as the square of something or the cube, I don't remember. Here's another example 1, but it does use that scenario. If W is inversely proportional, K over, to the square of V. If W is inversely proportional to the square of V, and W is 3 when V is 6. W is 3 when V is 6. Find W when V is 3. Find W when V is 3. That should be a 2. Okay, so if W varies inversely as V squared, and when W is 3, V is 6, find W when V is 3. So you end up with 3 equals K over 36. And as I solve this, I'm going to find out that K equals 108, right? If I did my arithmetic correctly. Okay. So to solve for W, all I have to do now is plug in my K value, which goes on the top. 108 divided by 9. 108 divided by 9. And you should have been able to obtain a value of 12. Okay? Those are 3 samples for example 1 of inverse variation. Okay? Joint variation. Joint variation. The second half of this adventure. Joint variation. Here's the way I understood it. A number varies directly as the product of 2 or more items. Okay, for example, we already have y equals mx. That was our example of direct variation, right? Well, Today, what if it's y equals, and then they're using letter K, K, X, Z, some other business. And it could be multiple items. Oftentimes you'll make a plan, and your plan will depend on this, that, and the other. That would be a joint variation, right? I'll be able to drive you home if my mom doesn't have to work and there's room in the car, right? That would be two things, joint, that would predict whether or not why I could take you home, okay? So let's do your example. If I do the example, I think you'll feel a whole lot better about it. Okay. Example 2. It says, if Z varies jointly as X, okay, and the square root of Y. Okay, so these two things, we're not inverse right now. We're just like direct variation. Z varies jointly as X and the square root of Y, and Z is 6 when X is 3, X is 3, and Y is 16. And I got to put my K in front of it because we've got to find our constant. If Z varies jointly as X and the square root of Y, and Z is 6 when X is 3 and Y is 16, so we're searching for our K. Find Z when X is 7 and Y is 4. Okay? So this is the scenario we're going to use to solve for K. Once we have K and plug it in here, multiplying it by 7 and obviously 2 will produce our Z value. So here's what I have to start with. 6 equals 3 times 4 times K. 6 equals 12K. K is a half, right? Hopefully you're able to see that. If I know K is a half, then I can solve for Z. Z is equal to 1/2 of 7 times 2, which is 14, right? Would you say half of 14 is 7? So when you are doing these, the critical component that for me was tough to wrap my arms around was recalling that there is a constant that you have to uncover with inverse and joint. Okay, direct variation, it's easy to solve it using proportions, but inverse and joint variations requires that you know the constant of proportionality, which in today's lesson is defined as K. That's example 2. What do you guys think of that one? I want to do a word problem with you. It's for example 3. This is the toughest one to understand, so if you've checked out, you might want to check back in. Example 3 is, what if you have joint and inverse combined? Then how do you solve that relationship? Well, reading what they say to you and then interpreting it is going to be the easiest way to read it. So look at example 3 with me. The electrical resistance of a wire varies directly as, I'm going to plug in my K, its length, and inversely as the square of its diameter. So I can put diameter squared underneath because it's inverse. Okay? Resistance of a wire varies directly as its length and inversely as its diameter squared. So the inverse item goes down. Let's see what data they give us. 100 meters of a wire, that's a length, with a diameter of 6 millimeters, has a resistance of 12 ohms. meters of wire with a diameter of 6 has a resistance of 12 ohms. 80 meters of a second wire with the same material has a resistance of 15 ohms. Find the diameter of the second wire. So once I get K out of this thing, and I plug in here, I'll be able to solve for diameter. You're used to seeing the variable after the fraction, and if you choose to write it that way, that's fine too. So let's go ahead and solve for K. I'm going to rewrite it over here so I have some more room. 12 is equal to 100 over 36 multiplied by K. 100 over 36 multiplied by K. The coefficient usually gets divided out, but you can't divide by a fraction. Multiply by its reciprocal. And some of you might reduce it and do it that way. That's fine too. I'm just not making it any more difficult. The result on the right, as all those numbers cancel out, leave me with K. The result on the left, after reducing this by a factor of 4, you end up with a K value of 108 over 25, which some of you might be looking at this saying that just doesn't seem right. Just bear with me so far. I promise you we're going to make this work. Okay? The K value of 108 over 25 is going to get plugged in to that equation in the position where K belongs. Okay? K goes here. 15 equals 108 over 25 multiplied by 80 over D squared. Okay? Multiplied by 80 over D squared. There's a couple of different ways you can work this using the arithmetic that you know how to do. I really don't care how you do it. I do it simple. I cross cancel by a factor of 5 and 16. And then I end up with the product of 108 and 16 over the product of 5 and D squared. All of that being equivalent to the ohms of 15. Whenever you're solving for a variable that's in the denominator, you multiply by the denominator to clear your fraction. You now have 1728 being equivalent to 15D squared. It gets easier to solve from here. That's 15 times 5. Dividing 1728 by 75, you get a result for D squared, which looks something like this. The square root of whom is about 4.8. And they're searching for millimeters. Top of the next page. They worked it a little bit differently. And it doesn't matter how you prefer to work fractional coefficient problems. You've learned a lot of different methods. Some of you do it in ways I can't even understand. But the key is to get your answer. Solve for K. Plug in your K value. Solve for D. And you have your answer. These take practice. They're not horribly difficult.